Look around the tech world today, and you're going to notice a pretty massive irony. Our digital AI, the intelligence behind chatbots, code generators, digital art, is undeniably incredible. It's just feasting on mountains of text and pixels, growing smarter literally by the minute. But our physical robots, they are essentially starting. We basically built this absolute genius brain in a jar, but it has no idea how to actually move its own hands. Welcome to this explainer on the Embodied AI data pyramid, where we're going to unpack exactly why our physical machines are lagging so far behind our digital ones and how the industry is frantically racing to fix it. So, you've probably wondered this yourself. AI is booming, right? So why exactly are robots starving? Like, why can't we simply take our smartest foundation models, the ones passing the bar exam and writing complex software, and just drop them into physical machines? Well, a brain in a jar doesn't naturally know how to walk. To make your robot move, balance, and actually interact with the physical world, you mean physical, embodied data. And harvesting that highly specific type of data is a completely different ballgame than just scraping a bunch of text off the internet. Okay, let's dive into this by defining the structural framework the industry actually uses to extract this new gold. We call it the data pyramid. It's a three-layered framework of data sources used to train physical robots. Those three foundational layers are real data, simulation data, and video data. And understanding the unique strengths and weaknesses of this exact pyramid is absolutely crucial if you want to understand the modern race to build functional humanoids. Here's our roadmap for today. We'll start with the embodied AI bottleneck, move through real robot data, simulation data, and internet video before finally looking at flipping the data flywheel. Let's jump right into Section 1, the embodied AI bottleneck. The fundamental problem we're facing right now is this. Sourcing high-quality robotic data is extremely difficult. Think about it for a second. Text and images, they exist absolutely everywhere online. We've spent decades happily digitizing human knowledge. But high-quality data that perfectly maps physical movement, like knowing exactly how much pressure to apply to an egg so you can hold it without instantly crushing it into an omelet, that is incredibly rare. The exact torque you need to open a jar, or the tiny subtle adjustments you make to balance on a rocky path, those things are painfully hard to capture in a format that a computer can actually understand. Moving on to Section 2, Layer 1, Real Robot Data. We're starting at the very top of our pyramid here. So what exactly is real robot data? This is data recorded when human operators remotely control physical robots to perform specific tasks. This is a process called teleoperation. Imagine strapping on a VR headset and haptic gloves, and you're manually controlling a robotic arm to, say, fold laundry or pick up a mug. You're basically puppeteering the robot. And as you do this, the system is perfectly recording every single sensor, every joint movement, and every camera feed in real time. But this premium layer comes with a pretty brutal trade-off. On the plus side, it yields authentic, ground-truth information. It perfectly maps human intent to physical robotics, making it the absolute core raw material for actually deploying robots in real physical environments. The AI knows exactly what to do, because a human physically guided it through the motions. But the cons? Oh man, it is painfully slow and prohibitively expensive. You just can't scale this exponentially because you are constantly bottlenecked by massive hardware costs, facility space, and the sheer limits of human labor. It's just physically impossible to scale this kind of one-to-one data collection fast enough to feed today's massive AI models. To overcome those severe bottlenecks, we're seeing some fascinating trends, especially led by companies in China like Agibot and G1. They're tackling the bottleneck by literally building massive data collection factories. By leveraging domestic labor advantages, they can have huge rooms packed full of human operators manually piloting robots all day long. It's this massive brute force approach to producing this premium top-layer data at scale. They're basically just throwing sheer human effort at a profound data shortage. Let's step down to Section 3, Layer 2, Simulation Data. Since real-world collection is so intensely constrained by the limits of physics and hardware, simulation data takes a different route. This involves training AI in physics engines and virtual environments. Instead of building a million physical robots to try and fail over and over in the real world, developers just plug the AI models into a virtual matrix. It's exactly like Neo learning Kung Fu in a simulation. The digital brain can practice its movements in a simulated physics engine completely safely millions of times and entirely in software. The incredible advantage here, for sure, is infinite scalability. You can spin up thousands of virtual robots all at once to generate millions of edge cases that would be way too dangerous, expensive, or just rare to capture in real life, like a robot carrying a heavy box slipping on a patch of ice. Tech giants like NVIDIA are making massive bets on this, and we've already seen wild breakthroughs, like a ping-pong-playing robot trained entirely in pure simulation. But of course, there is a massive catch to relying purely on virtual worlds. We call that catch the fatal dual gap. First, we have the sim-to-real gap. This basically means virtual policies often totally break down when faced with the messy, unpredictable physics of the real world. A robot might walk perfectly on flawlessly flat virtual concrete, but the second it steps on a real-world living room rug, it instantly falls over. Second, there's the real-to-sim gap. There is just immense engineering difficulty in accurately modeling the chaotic real world into a virtual engine in the first place. Think about trying to simulate the exact friction of a wet towel or the random shifting weight of a bag of groceries. The physical world is just too chaotic to perfectly digitize, and when those virtual brains meet real physics, they often break. Which brings us to Section 4, Layer 3, Internet Video. We are now stepping down to the foundational, bottom layer of our data pyramid. Internet and human-centric videos are without a doubt the most abundant and lowest-cost raw materials available to us today. Think about every cooking tutorial, every DIY video, every daily vlog you've ever watched. To an AI, that is millions upon millions of hours of humans simply moving, interacting with objects, and navigating the physical world on camera. This makes everyday video the absolute cheapest data mine in existence. But you really have to understand the fundamental trade-off of this specific layer. On the pro side, we have unmatched, truly global scale. Video helps foundation models build basic physical cognition. They learn how the world works, they pick up spatial reasoning, and they understand human intent. But look closely at the cons. Video completely lacks physical force, torque, and tactile feedback. A video shows the AI the result of an action, the what to do, but it completely fails to provide the exact motor signals of how to physically move its joints to actually accomplish it. Watching someone bake bread on YouTube doesn't magically teach you how the dough actually feels in your hands. Despite that pretty massive flaw, the tech world is absolutely swarming this layer right now. We're calling this the Silicon Valley pivot. Pioneers like physical intelligence, Figure AI, and Sunday Robotics are aggressively pivoting here. They want to bypass all that heavy, expensive teleoperation we talked about earlier by using reinforcement learning. They're crowdsourcing egocentric video, meaning first-person, GoPro-style footage of humans just doing everyday chores. In fact, projects like Apple's EgoDex and NVIDIA's EgoScale are aggressively building tools to extract high-signal, usable physical action data from cheap, everyday human videos. It's a real game-changer. Finally, let's move to Section 5, Flipping the Data Flywheel. When we step back and look at the pyramid as a whole, the landscape becomes really clear. Real robot data is heavily expensive with low scalability. Simulation sits at medium cost with infinite scalability, but suffers from that fatal dual gap. Internet video has the lowest cost and infinite scale, but currently lacks those crucial motor signals. It's obvious no winning model is going to rely on just one layer. But if you look at that bottom row, internet video holds a unique and incredibly powerful economic advantage over everything else. Because consumer video is so incredibly cheap and abundant, it's really the only layer capable of flipping the data flywheel. What that means is you take a robot, put it in the real world, let it try and fail at a task, and then use that cheap video data to instantly correct it. This creates continuous, infinite learning loops. It's literally the only layer with a low enough barrier to entry to actually sustain the true AI evolution needed for massive real-world deployment. I love this quote because it perfectly captures the race happening right now. Whoever cracks consumer-scale structured human video quietly powers every humanoid above them. This is the holy grail of modern tech. Mastering this messy, abundant video data and successfully translating it into precise physical action is the skeleton key to the entire robotics industry. It's the infinite raw material that's going to unlock and power everything else we build. So I'll leave you with this final thought to consider. When that data flywheel finally flips, how fast will our physical world change? Because once this foundational data code is broken and robots can finally translate cheap, endless video into perfect physical motion, humanoid robots aren't just going to be a cool novelty in a lab anymore. They'll be everywhere. Thank you so much for joining me for this explainer, and definitely keep your eyes on that bottom layer of the pyramid.